Today, you and I are going to build a simple neural network together. We're going to understand line by line what every single line does, and we're going to do something that no other video does, but everybody working on neural networks does, which is we're going to debug that model together and find an issue with it and make it work. For your first neural network, it's very traditional to use a data set called mnist, which is a handwriting data set. So our goal here is to look at digits that people actually wrote down of different numbers, and our classifier is going to try to figure out from those pixels what number the person wrote down. So I'm a huge believer in learning by doing, so I strongly recommend at this point opening up a terminal of your own and following along. So first, open up a terminal and type git clone https://github.com/lucas/ml-class. This will put all the files I use in all the classes in a directory for you called ml class. And by the way, you're welcome to modify and use these files in any way you like. Now type cd ml class, and then type pip install -r requirements.txt. This will install all the necessary Python packages. Sometimes students have trouble here. Usually this comes from needing to install a new version of Python. Now type cd videos and then cd intro to go into the directory for this class. There's actually one more step to track your work online. Type WNB signup. Just for reference, WNB is a product that I built, and you can create a free account, and then WNB will let you see your progress as you build the models. And since I built this product, we're going to use it heavily during all these videos. There's one more thing we should always do before we start, and that is to look at our data. So you can open up the file mnist.png, which I put in this directory, so you can see some of the examples of the digits we're going to classify. mnist is a famous data set of handwritten numbers from 0 to 9, and our goal here is to produce a model that takes a single 28 by 28 image and outputs which digit was written. This is a super practical task that's generally known as optical character recognition. There are lots of ways we could approach this problem. Today, we're going to use a type of machine learning called a neural network, and we're going to start with the most basic type of neural network, which is called a perceptron. I had to introduce a bunch of scary sounding terms here, so don't worry if these terms are confusing. They'll become second nature as soon as we start to work with them. Generally, perceptrons take in an array or list of numbers and output a single number. And just for now, let's slightly simplify our problem to just detecting 5s in our data. So here, the input numbers are pixel values, and we want the output of our perceptron to be a 1 if the digit is a 5, and 0 if our digit happens to be any other number. A little history. Perceptrons were actually invented in 1957 by a psychologist named Frank Rosenblatt, and they were originally designed for a very, very similar image recognition task to the one that we're actually doing right now. And I really like to imagine the machine that Rosenblatt actually built. He had an array of light sensors that would look at the image, and then he would pass the output of each light sensor through a system of dials he built, and the output would actually be either a light bulb lighting up or a light bulb staying dark. And at first, the weights, aka the knobs, were set randomly. He would put in a picture of a 5, and then the 5 sensor probably wouldn't light up. Since the picture actually is of a 5 and he wants the sensor to light up, he would try to get the output to be high. So how does he do that? He turns a random knob a little bit and sees if the light gets brighter. And if the light does get brighter, he turns it some more. If the light gets dimmer, he tries turning the knob in the other direction, and maybe it gets brighter. Then he moves on to the next knob and does the same thing. Once he's actually gone through all the knobs, he puts in another picture. Now, if this new picture is not of a 5, he now doesn't want the sensor to light up, so he turns the knobs in order to make the light actually be dimmer for this picture. Now, changing the knobs might mess up the settings for the first picture, but we don't actually worry about that for now. He keeps walking through all of his pictures, turning the knobs until he's looked at every single image of either a 5 or not a 5. At this point, he's done what's known in neural network training as an epoch. Once he's gone through every single picture, he starts back over at the beginning for a new epoch. These days, we usually think of perceptrons as an algorithm more than a machine. So let's talk about the algorithm mathematically. It's actually super simple. First, we take in a set of input numbers, which in our case happen to be pixel values. Then we flatten out the pixel values into one long fixed length array. Then we multiply each input by a corresponding number known as a weight, and we add up the results of the multiplications. These weights are those knobs, and they're somehow learned, but we'll go into more about that later. Sometimes we apply what's called an activation function to the output, but we actually don't need to worry about that now. And then finally, we can interpret the output number however we want, but in this case, we've agreed that we're going to say a 1 means that the output is a 5, and a 0 means that the output is not a 5. So let's do this on a very small, very specific example. Imagine, for simplicity, that our input images were 2 by 2 images. So here we only have 4 pixel values, and 0 corresponds to a black pixel, and 255 corresponds to a white pixel. We flatten the image out into an array that's going to have length 4. And now our weights happen to be these 4 numbers here, starting with 0.12. Where do those weights come from? We pick them randomly, but we're then going to learn them when we do our algorithm training. So finally, our weighted sum in this case is 2.55. If you're like me, this all becomes much more clear by hacking on it. So let's actually go to the code. Go back into your directory and open up perceptron-single.py in your text editor. Now let's walk through this. The first couple lines are just importing the library Keras, which is a fantastic library for building neural networks that we're going to use extensively. Now, the next few lines set up W and B, which we're going to use for actually looking at our results. Line 16 is the first interesting line, which uses a special Keras function to load the mnist data into 4 datasets. With a normal dataset, we'd have to download it and load it ourselves, but mnist is such a famous, well-known dataset that it's built into the Keras library itself. We're going to use a common notation in machine learning where X stands for the inputs and Y stands for the outputs. So here, X_train is a list of 60,000 28 by 28 images. Or another way of looking at it is that X_train is 60,000 28 by 28 array of integers from 0 to 255, where 0 is the darkest black and 255 is the brightest white. Y_train is a list of 60,000 labels, which in the case of mnist are actually digits between 0 and 9. Now X_test is a held out set of 10,000 images that we're going to use to test our algorithm on once we've trained it, and Y_test is 10,000 more labels that correspond to the images in X_test. Just for now, we're only going to classify 5s versus not 5s, so we have to transform our output data into that. Lines 18 and 19 create 2 new variables, is_5train and is_5_test, that correspond to exactly whether or not our image is a 5. Lines 22 and 23 calculate the image width and the image height using an incredibly useful function, shape. X_train.shape gives us the dimensions of our X_train variable, which, as we mentioned earlier, is 60,000 by 28 by 28. So X_train bracket 1 and X_train bracket 2 are actually both 28, since our images are, in fact, 28 by 28 pixel squares. Okay, now for the important part where we build our first neural network. Line 26 sets up our network to be sequential. Keras actually has different ways of defining neural networks, and sequential is the simplest and most important, so we're going to use it. It means that our network is defined as a series of steps. Line 27 defines this first step in our network, which simply flattens our data from a 28 by 28 two-dimensional array to a single 784 length one-dimensional array. We tell the flatten command that the input will always be 28 by 28, and this is a fundamental constraint of neural networks. The input size always has to be the same. If we ever have a different sized image, we're going to have to crop it or resize it before we feed it into our network. Line 28 adds a single perceptron to our network. The layer is called dense because every input is connected to every output, and this will make more sense later as our networks get more complicated. Our simple network outputs one single number, which is where that number 1 in line 28 comes from. Now, line 29 sets up our network for training, but this really requires some explanation. Our network looks like this. We are multiplying our pixels by a set of weights and adding them up and hoping that we output a 1 where the input is a 5 and hoping that we output a 0 in all the other cases. The only thing we can change about our algorithm is the weights. So how do we find a good set of weights that will output a 1 when our pixels correspond to an image of a 5 and 0 otherwise? We talked earlier about how Rosenblatt, the inventor of perceptrons, was turning knobs himself to train an algorithm. And I think, in fact, that's an excellent intuition for how all these algorithms work. However, if we actually had to try turning each knob and testing how well the network would work, it would take forever to train large neural networks on lots of data. So luckily, there's a computational method with neural networks that means we don't actually have to turn every knob. And in general, the problem of searching over a large number of knobs or parameters for an optimal setting is what's known as a gradient descent problem, and mathematicians have actually been thinking about this class of problems for hundreds of years. In this case of neural networks, there's a special optimization called backpropagation, which helps us calculate exactly what's going to happen when we turn each knob very, very efficiently. And this optimization is really important because we're going to change these knobs or these weights quite a bit. Since every machine learning library, including Keras, has a large array of excellent gradient descent algorithms built into it, we're not going to go exactly into how gradient descent and backpropagation works beyond this intuition, but there's a ton of materials online if you're interested in that sort of thing. I'll say my favorite resource for this is the 3 Blue, 1 Brown series on neural networks, which covers a lot more theory than these lessons and is also a lot of fun. Okay, let's go back to the code. There's 2 things we actually do need to define to make gradient descent work. The first is the loss function, which is basically how much we don't like our output, or how different our output is from the output that we wanted. The simplest loss function is mean absolute error, which is just how different your output number is from the output number that you wanted. A fancier loss function would be mean squared error, which is how different your output number is from what you wanted squared. And we'll use that for now. Here, MSE is short for mean squared error. The second thing we have to specify is which gradient descent algorithm to use. One really crucial and sometimes hard to set up parameter in gradient descent is called the learning rate. And this is basically how fast you're changing the weights every time you feed it a new image from your data set. Change the weights too slow and it'll take you forever to find good weights. Change the weights too fast and you might jump over a good set of weights. The right learning rate can really depend on the problem and other factors. There are many choices of algorithms in Keras, but I almost always use the atom gradient descent function because I don't have to specify the learning rate and it can really adapt to a wide range of cases. So that's what optimizer equals atom means. The final thing I do is I set the metric to accuracy. This doesn't change the algorithm itself, but what it does is it makes Keras output the accuracy of our algorithm as the algorithm learns. The last line here in our code does the actual training. We call fit on the model, which makes it look for the best set of weights given the input training data x_train and the output that we want, which is is_5_train. We ask our model to print out the accuracy on a held out validation set in addition to the training set that it was trained on. By default, Keras will do the training for 1 epoch, meaning that it will look at each input exactly 1 time. But here we set epochs equals to config that epochs, which we earlier set to be 10, so it'll actually go over each training data point 10 times. So now this model is super simple, but it will run. So go back into your terminal and type python perceptron-single.py, and this will train the network. You can follow the link to see a chart of the accuracy as the model trains over time. And wow, the accuracy of this model looks terrible. I would expect that just guessing would give an accuracy of 50%, and guessing not 5 only would give an accuracy of 90%. One really frustrating thing about working with neural networks is they never give you helpful errors. What they do instead is they just don't work that well. Most tutorials skip over the debugging part, but I think debugging is where the learning happens, so let's try to fix this model together. If you really want to learn, maybe pause this video for a minute and dive into the Keras docs and see if you can debug this yourself. So first, let's see if this model gets better with more training. We can set the number of epochs to 100 and wait a while. Okay, so we're back, and we've trained for 100 epochs, and you can see that the loss number really isn't going down at all, and the accuracy is not going up, so this model is definitely not improving. So the next thing we need to test is if the model can learn to fit a tiny subset of the data. So for time's sake, we're going to set the epochs back to 10, but then the important thing is we're going to set the input data to be just 20 images. So we subset x_train to just the first 20 examples, and then we subset our output data to be just the first 20 labels. Now, a reasonable neural network should be able to get 100% accuracy on the first 20 images just by overfitting. So we run this neural network, and we pull open the output in weights and biases, or W and B. And we see that the accuracy is still not good, even when we're constrained to just the first 20 images. So something is really broken. So the next thing to try is to look at what the model is outputting on just a couple of test images. So x_test is a set of test images, so we can call print on model.predict x_test:10, and this will show us what the model is actually outputting, the number coming out of the model on the first 10 images. And this is pretty weird. So we were expecting numbers between 0 and 1, but we're getting numbers that are wildly negative and numbers that are above 200. So remember, nothing ever said that a neural network had to output a number between 0 and 1. So we'll get into this more deeply in later episodes, but remember how we said you can optionally add an activation function to the weighted sum of the perceptron? Well, here's a really good reason why. We want to force our output to be between 0 and 1. And now, a common activation function, maybe the most common activation function, is called a sigmoid, also for you math nerds colloquially known as logistic or softmax. For you non-math nerds, the important thing to know about a sigmoid is that big negative numbers are turned into zeros, and big positive numbers are turned into 1, and numbers near 0 are turned into something in between. So no matter what your weighted sum is, the output after taking the sigmoid is going to be between 0 and 1. So we can add a sigmoid by going back into our code and adding just a single line to our model, which is activation equals sigmoid. On a small data set, the loss is going down and the accuracy is going up. So this is a really good sign. So let's go back in and let's train the model on the complete set of training data again and see how well it does. So now our accuracy is closer to 91%. So we're doing better than random. So as an aside, whenever you're building machine learning models, you basically have 3 ways to make your models better. You can improve your algorithms like we're doing now, which tends to be really hard, as you can see. You can improve your data preparation, which is also pretty hard, and we'll talk about that more later, or you can add more training data. Adding training data might seem hard, Labeling 60,000 images probably took a long time, but I actually started a company called Figure 8, which will do this for you, and you should check it out if you need more labeled data. This model is working reasonably well, but actually every time you run it, you're going to see different scores. So when you train this model, you may get a different accuracy number than I'm getting. We'll get into how to fix this and how to build much more complicated models in the next installment. What did we cover today? We built our first neural network, and more importantly, we debugged our first neural network. Get used to that if you really want to build neural networks for your job. We also talked about Keras, which is the most important neural network framework, not just for beginners, but people that really build neural networks professionally. And we talked about loss functions, and we talked about weights, and a little bit about backpropagation. In the next section, we're going to take this neural network and we're going to build what's known as a multi-layer perceptron, which is a more complicated neural network that can do more things. And then later on, we're going to build a convolutional neural network, which is maybe the really fancy kind that you hear about in a lot of papers and in the news all the time. And we're going to keep creating these videos, so you should probably subscribe so that you're the first to know when a new video comes out.